Hello! In a previous lecture, we proved that all impartial games that are losing games are equivalent to star 0, the NIM game with no chips. In this lecture and the next one, we will take this a step further and prove that every NIM game is equivalent to star n for some n. That is, we will show that every NIM game is equivalent to a NIM game with a single pile. We will also find a strategy for playing NIM. Now, ultimately, we want to prove that every impartial game, not just NIM games, is equivalent to a NIM game with a single pile. So here is a definition that will be useful. If G is a game such that G is equivalent to star n for some n, then n is called the nimber of G. For example, any losing game has nimber 0. That is something we proved earlier. Now, as an exercise, show that the notion of nimber is well defined. That is, it is not possible for a game to have more than one nimber. The key theorem that is needed to calculate nimbers for NIM games is the following. Suppose n is equal to 2 to the a1 plus 2 to the a2, etc., where a1 is greater than a2 greater than the rest. Then, star n is equivalent to star of 2 to the a1 plus star of 2 to the a2, etc. Now, at first glance, this looks like a bizarre theorem. It links star n with the decomposition of n into powers of 2s. We will prove this theorem in the next lecture. For the rest of this lecture, let's have a look at some of the applications of this theorem. We start with an example. We first write 11 and 13 as sums of powers of 2s, like this. Then, using this theorem, we have these equivalent games. So star 11 plus star 13 is equivalent to the sum of these two expressions. We now use associativity and commutativity to rearrange our expression like this. We group identical terms together. Then, we can use the copycat principle to reduce identical pairs into star 0. This simplifies down to star 2 squared plus star 2 to the 1. Since these terms are distinct powers of 2s, we can apply the theorem again to say that this expression is equivalent to star of 2 squared plus 2 to the 1, which is star 6. So the number of star 11 plus star 13 is 6. Now take a few moments to think about where do we get the 6 here, and how is this related to 11 and 13? Or in general, how can we find the number for star b1 plus star b2 to star bn? Well, we certainly are looking for binary expansions of each bi. The copycat principle is going to cancel any pair of identical powers of 2s. So what remains would be the powers of 2s that appear in odd number of expansions of the bi's. Now, one way to visualize this is by using binary numbers. We can write the numbers out in binary. In this case, 11 in binary is 1011, and 13 in binary is 1101. We then take the XOR operation. That is, normal addition, except we do not carry over. So 1011 XOR 1101 is 0110. A shorthand for this operation is a plus with a circle around it, and I will just say this simple as plus. So 11 plus 13 is 6. Let's look at another example and consider star 25 plus star 21 plus star 11. Take a few moments to work out what would be the nimber for this game. So in binary, 25, 21, and 11 are 11001, 10101, and 01011. Then the addition of these three numbers using the XOR operation is 00111, which is 7. So star 25 plus star 21 plus star 11 is equivalent to star 7, and the nimber is 7. Generalizing this process gives the following result. Star B1 plus star B2 plus all the way up to star Bn is equivalent to the star of B1 plus B2 plus all the way up to Bn. This result tells us that every nim game is equivalent to a nim game with one pile. So, in particular, every nim game has a nimber. So why do we care about reducing a nim game down to one pile? As it turns out, we can find a winning strategy for nim in this way. Let's have a look at our previous example. Star 11 plus star 13 is equivalent to star 6. This is a winning game, so now we want to know, how do we find a winning move? Now, a winning move should result in a losing game. So what we want is to move to a game that is equivalent to star 0. One way to get star 0 is by adding star 6 to both sides. So this gives us star 11 plus star 13 plus star 6 is equivalent to star 6 plus star 6, which is equivalent to star 0 by the copycat principle. Now we started the game with two piles star 11 plus star 13. But now we have a game with three piles star 11 plus star 13 plus star 6. This is not a valid move in nim. One way to avoid that is by grouping star 6 with the star 13. So let's consider star 11 plus the group of star 13 plus star 6. We can make a quick calculation to see that 13 plus 6 is equal to 11. So this is now equivalent to star 11 plus star 11, which is a losing game as we wanted. So what is the winning move? We start with star 11 plus star 13 and move to star 11 plus star 11. So we are removing two chips from the pile of 13. Let's have a look at a second example. Star 25 plus star 21 plus star 11. And this game is equivalent to star 7. So we will add star 7 to both sides. This time, we will pair star 7 with star 21. And we see that 21 plus 7 is equal to 18. So then, this is equivalent to star 25 plus star 18 plus star 11. So the winning move here is removing three chips from the pile of 21 to make it a pile of 18. Now you may be wondering, why are we pairing star 7 with star 21 instead of the other two piles? So what happens if we pair star 7 with star 25 or star 11 instead? Well, we see that 25 plus 7 is 31, and 11 plus 7 is 12. So if we pair the 7 with the 25, then star 25 becomes star 31, meaning we are adding 6 chips to the pile of 25. Or in the second case, we are adding 1 chip to 11, and these moves are not allowed in nim. So then the question is, can we always pair up the nimber with an existing pile so that the size of the pile goes down? And the answer is yes. And here is our lemma. If star B1 plus all the way up to star Bn is equivalent to star S, where S is positive, then there exists some Bi where Bi plus S is less than Bi. We will illustrate the idea of the proof using our example. So the main idea is that we are looking for the largest power of 2 in the binary expansion of S. We have star 25 plus star 21 plus star 11 is equivalent to star 7. And in the binary expansion of 7, 4 is the largest power of 2. This means that at least one of the three numbers has 4 in their binary expansion. In this case, we see that it is 21. Now let's look at what happens when we add 7 to each of these three numbers. When we add 7 to 21, we see that entry at 4 would disappear. So 4 is subtracted from 21. On the other hand, for 25 and 11, 4 is not part of the expansion, so 4 is added when we add the 7. Now what about the rest of the terms, the 2 and the 1? Well, we see that 4 is greater than 2 plus 1. So if we look at 21 plus 7, we see that 4 is subtracted from 21, but the remaining terms adds at most 3 to this number. So overall, 21 plus 7 will be less than 21. On the other hand, if we look at 25 plus 7 or 11 plus 7, we see that 4 is added, but the rest of the terms will subtract at most 3 from the terms. So the resulting number will increase 25 or 17. So we will pair up S with the number whose binary expansion contains that largest power of 2 in S. And that is the basis for our proof of the lemma. Suppose S is equal to 2 to the A1 plus 2 to the A2, etc., where A1 is greater than A2, etc. Then, 2 to the A1 appears in the binary expansions of B1 to Bn an odd number of times. In particular, there should be at least one. So let Bi be one of them. Now suppose that star Bi plus star S is equivalent to star T for some T. Since 2 to the A1 is in the binary expansions of both Bi and S, 2 to the A1 is not in the binary expansion of T. For the rest of the terms, to the A2, to the A3, etc., at worst, none of them are in the binary expansion of Bi, so all of them are in the binary expansion of T. So T is at most Bi minus 2 to the A1 plus the rest of the terms to the A2, to the A3, etc. And this is less than Bi because 2 to the A1 is greater than the sum of the remaining terms to the A2 plus to the A3, etc. So that completes our proof. Now this proof also gives us a way of finding a winning move in a winning game. Say a game has number S. We look at the largest power of 2 in the binary expansion of S. We then pair it up with any pile star Bi, which contains this power of 2. Then our lemma tells us S plus Bi is strictly less than S. So a winning move is taking away Bi minus S plus Bi chips from the pile of star Bi. So that gives us the winning strategies of winning nim games. Now remember that all these results are consequences of the main theorem from earlier. And we will prove this main theorem in the next lecture.